sure it's somewhat acceptable for stream. Yo, we got some crazy energy drinks to try. Let's see what we got. Let's see if we're gonna start out with Amazon Energy. Ah, yes, perfect. It's rich in antioxidants. I don't really know what those are. Samba's on. It's like Samba. You guys know Samba? What? That's like the Microsoft. That's the NFS clone. Samba. Samba. Oh, opening windows to a wider world. Wow, that's a really nice slogan. There was a great Hacker News post yesterday about how the old internet wasn't really better. You just got older and everything sucks. And that's somewhat true. I somewhat agree with that. Alright, so I've been struggling all morning with memory. The thing that I want, the problem is basically this. I have, so my registers right now in this little version is a 4x4 2D array. And I have 64 block memories. Actually, do I even have 64? No, this isn't even right. I have 16 registers, 4x4, and I have 32 block RAMs. All right, and then the thing that you're building is a multiplexer. And it turns out that big multiplexer kind of hard. Big priority encoder, even harder. But this does synthesize. So for, people say that I'm not synthesizing anything. I'm synthesizing stuff. So we're gonna look and we're gonna see, okay. So the reason my memory architecture is so tricky is because it actually supports reads from any address. On the first clock cycle here, we fetch all the addresses by using, it's fully strided. So by strided, we can access anywhere in the memory array with 2 stride parameters. Now, these things are great. The problem is, memory's not really happy to do this. Memory likes to be accessed in big chunks, not small random chunks. This is universally true. Whether you're on a hard drive or an SSD or DRAM. Turns out it's even true for SRAM. Like, random access is just hard. So a lot of computers are just figuring out how to make your access not random, What do you think caches are? Well, I'm going to read a big chunk, load it into the cache, right? And then you have caches that are like 4-way associative. And I think what I'm asking for is a 2048 associative cache. Let's understand this first. No, I'm gonna make the whole thing work in this FPGA. Look, if I can't make it work in this FPGA, I shouldn't be spending $7,500. That's like the kind of people who think they're gonna become good musicians because they buy, an expensive microphone. You're not. Or you're gonna become a good hacker because you buy an expensive keyboard. You're not. If I can't make something work in that FPGA, then, what am I doing, right? That's the scam. Like Cruise is building, they're spending $5 billion on Cruise Origins. Why? You can't make it work in a Bolt, Oh, well, we want to be ready when it's time. No, this is bad thinking. macOS or LMAO? I'll choose LMAO. But seriously, shit like that is going to be a ban because we're here to talk about something. Fuck off with your dumb, well, do you like red or blue? They're both shitty and make purple. So yeah, the small one has enough gates. I mean, you can't synthesize the whole thing, but I should be able to synthesize something. By the way, our floats got nerfed. Our floats used to be 19 bits. Now they're 18 bits because BRAMs are 18 bits. So, if you liked your 19-bit float, I'm sorry, we stole a bit off of the Mantissa. So now they have 9-bit Mantisas and not 10-bit Mantisas. It's a Arctic 7 100T. Okay, so by the way, I've gotten two groups of people who've reached out so far about Cherry Computer. One group of people like sends in their resume and they practically start their email with greetings hiring manager. Like, there's no fucking hiring manager, it's me. I'm not reading your bullshit. I will read your pull requests if you contribute to TinyGrad. And I realized that I didn't make contributing to TinyGrad that easy, so I added some to do. So I've already laid out the RISC architecture here. This is the RISC architecture. These are the instructions you're allowed to use. These are the 14 TensorGrad operations written in the RISC architecture. But like not really, because like the backwards conv I just stole from, like this is the NumPy backwards conv. So I want you to write the rest of the operations. This on broadcast is using .sum, which is a NumPy thing. I want you to write the rest of the operations in RISC. So I'll show you guys what it looks like when you run it. Not calendar. Why would I ever want calendar? If I go over here to TinyGrad and I run it, we had a bunch of good contributors to TinyGrad, so I trust that people will be able to do this, right? So like here's a conv2d. This actually is going through the RISC. The sub is going through the RISC. The mul is going through the RISC. So is the add. I haven't done the reduces yet. And I haven't done the, don't worry about like slices and reshapes. Those are free. I haven't done the reduces yet, and I haven't done the backward pass for conv. So I leave that to you guys. If you're interested in working at Cherry Computer, contribute to TinyGrad. The other group of people who reaches out is investors. And the thing about investors is this. Capital is kind of worthless these days. If you notice that like there's an absurd amount of capital to fund every possible scam you could possibly imagine. So like, you know, I don't know if I'm actually going to do this yet. I'm certainly not taking your money. I'll only, you know, I thought about it. I was sitting in the tub yesterday. I'm like, when do we actually want to take money? Well, we don't actually have to take money to do any of this, to write all the FPGA code. And then for this, I don't know, I'll just do a Kickstarter for the card. All right? And then, like, we have the most valuable line investors. You know, you guys want the company to succeed because you want your card to be good. Right? Like, fuck off with your, like, oh, I'm a liquidity provider. Yeah, well, you know, liquidity is, like, useless because there's all the free money in the world. So that's kind of my thoughts on investors. You know, and yeah, if you're, this isn't like, you know, Comma needs some, like, physical stuff. It needs, like, cars. It needs, like if someone's a serious contributor who, like, starts contributing to my Verilog code and, like, buys one of these boards and gets it working on here, I'll buy you one of those cards out of pocket, you know? If you don't have $7,500, like, I'll just buy you one. If we get to that point. And then, like, yeah, I think we'll just put the cards up on Kickstarter. I think they'll sell. So yeah, the Kickstarter goal would be for 10 million, for 10K cards, it would be $10 million. No, it's not capitalism, right? What we have now has nothing to do with capitalism. The money is all fake, so it's not capitalism, right? Because there is no capital, right? Like you're playing for points, right? It's state capitalism. Like, you know, oh, what do the Chinese have? Well, state capitalism. What does America have? State capitalism. One day maybe we'll have real capitalism, but you know, in real capitalism, you don't have bailouts, right? You don't have PPP loans. You don't have unemployment. You don't have any of these things that are not capitalism. No, not ANCAP. No. You want governments. You know what would be nice? If we had some fucking protections against monopolies, right? Now, you can't have a company which has one profitable division that subsidizes their other 10 divisions perpetually. You can't do that, right? So it would be nice if the state took action against that instead of, you know, subsidizing corn, so we could have ethanol in the fuel even though it costs more energy to produce than it does to make, right? No. Unemployment? I mean, maybe there's private unemployment. You can probably get unemployment insurance if you want. But yeah, let it be private, right? No, we got to get, oh my God, the student loans, don't worry. No, the student loans can be private, but, the banks can ask you, hey, what are you going to major in? And if you say, like, well, I'm going to major in 15th century Russian history. And the bank's going to be like, all right, well, good luck paying for that. I'm going to major in petroleum engineering. Well, we're interested. So, no, it's not you either allow government intervention or you don't. No, it would be nice if we had a sane, but all right. This is just about why, like, no, I don't want your fucking money. Like, it's worthless, right? Like, and everyone with capital should kind of realize that, like, you are part of a class that's about to be, like eat the rich, man. Eat the rich. My coworkers at Comma got a big shirt that says "Eat the Rich," and I think "Eat the Rich" is a good movement. So yeah, I mean PCIe would be nice. I'm probably gonna have to write some like Ethernet thing to actually DMA in and out of this RAM when it's time. Like I'll write some little Ethernet thing which lets you access the memory through a backdoor. If you asked me on LinkedIn and it wasn't out on a date, I ignored your bullshit. UBI, it's just fucking bullshit, man. It's all bullshit. UBI, oh what? Oh yes, well just give the people money for doing nothing. That's a great idea. You know what? There was another group of people that did this and it was called Slavery 1.0, But now it says, all right, never mind. I don't want to go off on this, but UBI is fucking stupid, man. Like, you can't just give people money for not working, right? Because then what happens? You're going to be outcompeted by my society that decides not to give people money, and you can't contribute usefully to society. Well, bullets are cheap, man. Bullets are cheap. And that's what we did to the horses. Sorry. By bullets, I mean birth control. Yes, that's it. All right, cool. I think a $10 million Kickstarter goal is possible. Why not use an existing RISC core? Well, the hard part's not the RISC core. I wrote that in a day. I mean, yeah, we'll have to get like pipelining working, but still, like this is in order. Like pipelining is easy. I could do pipelining in a few hours if I decided to do it. But yeah, I mean, the stuff's in order, so we will have to get some like superscalar stuff up, but that's still a long time away. For now, I'm focusing on the feasibility of my instruction set. Now, everything else I've seen made before. I added Huawei to the blog post. And Huawei uses a 16 by 16 by 16 matrix unit. So we have a 32 by 32 by 32. So it's similar. That I trust I can build, but what we're going to look at now is we're going to understand the different memory architectures of these different things. Because it seems like my magical stride instruction is not that easy to build in hardware. Because you have, so the problem is basically you have, what I'm trying to make is a RAM that has 1024 ports. Right? And an SRAM with 1024 ports is just not something like, you can build. So I'm trying to like emulate it with some hardware around it. But kind of why you can't is an interesting question. SRAM with large number of ports is really what I'm trying to build. interleave lesser ported banks. True multi-port memory. Problem. No, see, the problem is if you try to fix any of this in software, like all these people are like, oh, well, if I just pack my memory like this, yeah, and then some like new little thing is going to come out, and like your memory architecture won't be efficient. You'll barely be able to get it run on your chip, which is like fine, but I don't know. Like I want to build something that has an instruction set that's just beautiful, right? Like, and strides are beautiful. Having to like, oh, okay, I have to make sure my memory is aligned on every 32-bit word. But if you're going to pack like this, I have to reorder my axes like that. No, I just want strides, man. Big strides. Okay. High area, energy, and delay cost for a large number of ports. 12 access ports. I want 1024. Oh, okay. Well, okay. It turns out people have come up with this idea before. So this is effectively what I wrote in Python with hashing. And I wrote this, like, you know, you can just read it. It's in Twitch core. It's called risc-v. So I wrote this hashing scheme thing, and I thought I was clever. Okay, well, so it turns out I didn't invent anything new, and it turns out that the thing that makes it hard, okay, weight arbitration delay is fine. Have to provide an interconnect between each requester and each bank port. And the problem is that's the problem right now, right? In the final edition, this will be this many registers and this many BRAMs and this many bits. And like, if your connection is just a single OR gate with 6 transistors, I've already spent 240 million transistors on my multiplexer for my SRAM. And now, maybe that's acceptable, but I'm not really sure. All right. Non-fucking Adderall. You know what? Are you ever going to contribute anything of value? Probably not. Get banned. All right, can we please stay on topic? It's not that there's cache thrashing, right? It's this. You can spend a lot of time writing these incredibly sophisticated cache-aware algorithms, but writing algorithms that are cache-aware takes a lot of software engineering time. So you can do it, but like it's just annoying. Yeah, I'll spend a lot of transistors on SRAM, but that isn't even SRAM. That's just my decode logic for my SRAM. Which seems kind of absurd because I'm going to spend all those transistors, like, how many transistors is an SRAM cell? Right? I've just, like, I could have doubled the size of my SRAM. Why do I need 1024? Because it's 32 times 32. And like it's squared, which is the killer. You gotta multiply that by that, right? So we can start sacrificing the stride. And that's why I'm hoping you guys out there are going to contribute to TinyGrad and get everything working in Risc. And you can use the strides for now. Feel free to use the strides. You'll see, like, here's my Risc implementation of a convolution. That's in ops Risc. I've already written a few paths to, like, optimize a little bit. And yeah, I mean, these strides are all small on the X dimension. These strides are all 1 on the X dimension. This one's using an H times W, but that's still relatively small. So I'd have to see what I could do to handle like small strides like that. Maybe there's something I could do. And then we'd have a restriction on one of the strides, and that might make things easier to build. What is H times W? So if your convolution is 3 by 3, it's 9, 5 by 5, it's 25. But yeah, so this code's all open source in the TinyGrad repo. You'll see that of the 14 TinyGrad ops, I've implemented the unary, the binary, and the processing. I have the backwards for matmul. I don't have the backwards for convolution yet. I'm waiting for somebody to implement that. And I don't have the reduce. I'm waiting for somebody to implement that too. What board should you use? You don't need a board. You can just do it with What's a stream buffered multiport? Organized memory to have a single wide port. I should understand this. This is an interesting idea. Oh no, this is the same. See, it relies on wide memory. So if your memory is wide, oh my God. Mental framework for hardware. You asked that question twice. It's a stupid fucking question. Like, think about why it's a stupid question during your timeout. Yeah, a lot of stupid questions today. Can we get some mods up in here to kill the stupid questions? Do I have any reference code for implementing the backwards function? This is a stupid question. You know, you ever seen the movie Clerks when they're standing around at the thing, and it's like, do you have any new movies? And the guy's standing right under the new movies. Do you know where the reference code is for the backward pass? It's literally right here. I wrote it in NumPy. Actually, I didn't write it, so this was contributed. No, UBI, George is mean. Yeah, well, do you want to be mean, or do you want to live in a society where people are nice but society sucks, or you want to live in a society where weak men, strong men times, you know? What's this? What's that? Like, yeah. Here we go. Yeah, hard times create strong men. Strong men create good times. Good times create weak men. UBI fuckers. Weak men create hard times. You are here. Now let's, do you want to live in a society where people are nice, but it sucks? Or do you want to live in a society where, right? Come on. No, this is like very basic memory stuff. This is more useful. A local cache. Use a cache coherence protocol. Yeah, okay, this is the one where you make copies. All right. Srytech banned. I'm not gonna stream anymore if you guys are gonna stay off topic. UDiver banned. See ya. I'm not gonna stream anymore if you guys are gonna ask stupid questions. Please focus. Alright. So let's take a look at what these other companies are doing. Let's take a look at Google's. Okay. Chapter 2, because it's easier to efficiently generate programs with 2 Brony cores per chip than numerous Wimpy cores. I agree with this. Vector unit and 8 megabyte VMem. The VPU streams data to and from the MXU through decoupling FIFOs. Okay, what did Google do for this? Bandwidth required to feed and obtain results is proportional to its perimeter, while the computation it provides is proportional to its area. Wait. Is that right? Oh. Huh. Wait, okay, let's understand what these matrix multiply units are actually doing, because they're not doing a full matrix multiply. But what they might be doing is it's like 128 times 120. Ah, okay. So you're loading in 2 vectors and it's giving you the multiplies of all of them. Well, this is cute. Can someone just rip off the Google TPU and build an exact copy of this? I don't like VLIWs. Get rid of that. Alright, they're using Brainfloat. Don't do this. What? No, I've seen all around 0. I don't know. I saw something else on this that was pretty good, but whatever. Of the 5 training startups, Samba Nova. Oh, did someone email me and tell me about this? And I thought, yeah. Okay. Oh, the Habana Gaudy. None of the 5 training startup has supported training accuracy or time to solutions. Habana got bought by Intel, so we know that that's not going anywhere. Can I buy one of these? Products. Okay, well, I wanted the white paper, but it disappeared. Gaudy training platform. Thanks for telling me about your ResNet 50 performance. Yes, everyone cares deeply about ResNet 50. Can I buy one? Why do none of these companies want to sell a fucking chip? All right, buy. Oh, sign up to receive Amazon.com. Habana. Why? Look at the top one. Yeah, the only AI accelerator card you can buy. Well, that's a lot of money for 2060. All right, I'll look at chat again if the, you know... Oh, I didn't know there's a TPU v4. Wow, there's TPU v4s. Oh, they put 4 chips, 4 cores per chip, TPU v3. One exaflop. Why doesn't Google sell the chips? You know, that's really what this comes down to. They made an Inference one too. Here we go, training. Wait, I didn't realize Alibaba has one too. Wait. It's just kind of interesting how... Oh no, Nvidia's getting fast ones too. Wow. All the fast ones are with MXNet. I didn't realize MXNet like still existed. Oh, TPU v4s. Oh, a paper just came out yesterday on the TPU v4. Cool. Oh. Wait, does the I stand for inference or industrial? Oh, inference only. Why is it inference only? Triple strided tensor DMA. Oh, triple strided. They did. Oh, see, I knew it was all about strided, man. Look, we had double strided, but Google knows what's up. I was just thinking about triple strided, you know, because you could do the convolution for the triple stride. Tensor DMA engines. What's an uncooler? Oh, I like this. Oh man, Google already solved all the problems. I just want to buy this. All right, we'll update the blog post. Can the government force Google to sell TPUs? Arbitrary steps per stride and positive negative stride distances in each dimension. Oh, but this is just for the DMA. What's CMAP? Yeah, I watched the Jim Keller interview. I don't know. I think the Tens torrent is, they're focused on weird stuff. Like they're talking about things like every AI startup that talks about sparsity. Like, yes, I understand why hardware people like sparsity, but there's no good research on this. And there's other like weird stuff that's just like not what normal people are training for networks. CMAP. Increased on-chip storage. The first concern of a DSA. What's a DSA? Domain-specific architecture, eh? Why can't it be used for training? What's the difference? Training needs large scale. Oh. So it's just that. Has anyone just ripped this off yet? Can somebody just... Oh, it's 7 nanometer too. Can somebody just rip this off, please? Oh, cool. This was yesterday. You bet they have the TPU v5 on 5 nanometer. I mean, yeah, that's possible. They still have the push to software issue. I mean, yeah. The thing about the push to look. Oh my god. Performance per TCO versus per CapEx. Why inference can need floating point? Yeah, like, how come none of the other startups are on this list? I could be on this list next list. The only thing available is Nvidia. Oh no, I can download it, but I'm just looking. I'm not even really sure. Like, picojoules per operation. Due to packaging innovations. Portions of a new architecture have been bound. Indeed, compiler problems likely sink the titanium. Yet many DSAs rely on VLIWs. This is the problem. Can we get Google's XLA compiler? It's an XLA to connect with cloud TPUs. Does this go all the way down to the instruction set, or does this just go to XLA? And then I feed it to some like secret Google service somewhere. It provides direct access to the TPU host. TPU VMs, they require an extra VM. TPU VMs, oh. Yeah, but it's not about hiring smart compiler people, right? It's about building an architecture where the architecture itself is good and you didn't just hack around it with your fancy software, right? Like it's building things that are actually powerful, not like, you know, well, if we carefully lay the things out like this, well, yeah, but then like some new architecture comes along and like yours is annoying to write for. Versus if you design something that's like generic and powerful, like think about chips that you can just make and scale, and you know the chips are going to be good, and when you want to do something new on them, it's like, oh, I can just write like a program to do it. I mean, these are modern computer chips. You know, if you ask the same question twice, I saw your question. What's a hardware instruction? Like, there's so much you don't know, and like I don't even know how to start answering that question. It's not that they're not good compiler architects. They are good compiler architects, but the problem is, like, if you have to put all this complexity in the compiler in order to make your hardware fast, it isn't actually good. And this is a lesson over and over again in like computer architecture that people just don't seem to learn. We're not using, look at the M1, right? What are people doing on the M1? They're running Chrome, right? Why are there no DSLs for Chrome? Why did nobody make a VLIW instruction set that includes, you know, things? And look, if we carefully compile the WebKit code, and like, it's the same thing. We don't do that for obvious reasons. Even though most of the time on all the M1s in the world is spent running web browsers. It's still doing all of that fancy, you know, out of order instruction execution. You're like, but oh, you could just compile it better. Well, yes, you could, but this doesn't happen in practice, right? Like occasionally what you'll get is, okay, for example, Intel has something called MKL, and Intel can speed up matrix multiplies. I don't believe NumPy by default is compiled with MKL. So you have literally billions of Intel CPUs out there, and they're not running Intel MKL. They're running, you know, the whatever NumPy crap BLOS translated from 7 Fortrans. You don't make it better by improving the compiler. You make it better by improving the hardware. And okay, you can say that, oh, well, but neural networks are different, right? And then really ask why neural networks are different. Well, people think neural networks are different because they, we have these like libraries like TensorFlow and PyTorch to use them, right? But when Google understands why TensorFlow sucks and why PyTorch is good, you'll also understand why VLIW instructions and custom compilers are bad, right? Like TensorFlow is this custom compiler. TensorFlow is this custom compiler that's going to globally optimize your ML networks. PyTorch looks a lot like TinyGrad. PyTorch wins. Look at something like Thneed, right? Like Thneed, look at Thneed on the Qualcomm, right? Like that's the kind of stuff you want to do, right? Like, okay, that's a JIT basically. Like JITs are great. Static analysis is bad, and it always will be. Right, so if these people are building JITs, fine. But they're not building JITs. They're building compilers. Like, really, you want to put your JIT right in the hardware. It's all, right? Well, what is your CPU running when it's doing all that out of order shit? It's a JIT, right? It's a JIT to go to your micro ops. It doesn't even cache. Who cares? This change meant it could take months of extra development to restore the quality score using integers that experts achieved in floating point during training. Yeah. Like, why don't you just put the floating points in? Oh, you have to understand an integer. If we do an int 8 multiplier, it uses this many less picojoules of energy. Yeah, but developers hate you. I don't know. You think about the mill CPU. Yeah, I've like heard about the mill CPU, and again, it doesn't exist. Low power, statically scheduled hardware. No. Bad idea. Dynamically scheduled, high power. Good. Informed memory management hardware. Oh God, my compiler needs to inform it of what memory it's going to access. You can't do this. You know, I really don't want to make a chip. I really don't want to do this. I'm not actually going to start this company, you know? Like, you just think about how much you actually have to do. It's so much. And, like, my hope is that this will convince the other companies to stop doing this bullshit. And they all do the same bullshit. It's as bad as self-driving cars. Hey, look, I'm an old man. You think I'm going to start a company? Just like two things. One, I don't care how shitty your chip is. First off, make it available for sale. And then second off, build chips that aren't shitty, right? If you don't do the first one, though, all is lost, right? Like Google's TPU might actually be great. I don't know anything about it. Right? Use a shared library called libtpu. Oh, libtpu. Download. libtpu.h. Oh, well, is this a special Google one? Where? That's not TPU code, is it? This is like XLA code. See one of the last demo slides. No, this is LVM. And that's Intel. No, we have to get libtpu. I wonder if we can download libtpu from somewhere. So my understanding is you can get the Edge TPU one, but the Edge TPU one is completely unrelated to the other TPU. You know, with all our new knowledge, that we could probably go back and we could probably understand the Apple neural engine a lot better. We could really understand what they've built. This is the book on computer architecture, eh? Microsoft Word in 30 minutes. Oh, but this just sucks. Like, well, why doesn't one of these companies build a good chip and make it available for sale? You know, I'll add tiny grad support if you make like, I don't really want to make hardware. It just sounds so painful. You know, like, you do it slightly wrong. Oh. You know, you like write some bug and then you're gonna have to, oh, your tape out's bad. And it sounds so stressful. Like making circuit boards a comma is stressful enough. No, I don't want fucking cloud TPU. I don't give my shit to Google. I hate Google. I will pay them double what it cost them to make the chips. Quadruple even. I'll pay them quadruple. I hate, you ever read, I think they changed it, but the original license agreement to Google Cloud said that you were not allowed to use it for like self-driving cars because it competes with Google. You couldn't use the ML stuff to train any services that could compete with Google. What a joke. You know, it's also why Google will never succeed at cloud. Nobody uses Google Cloud. We use Azure. A bunch of people use AWS because Microsoft and Amazon understand that they can't take all the value, right? Microsoft and Amazon, you know, like they both understand. They both have like customers, and they understand that they can't take all the value. Google takes all the value in advertising, and Google just like they think they can treat their customers like that, and they think they do that with cloud too. And like, you can't, and that's why they'll never succeed at cloud. Two port. No, I need 1024 port SRAM. Can I buy 1024 port SRAM? I'm not gonna. I can't make hardware, you know. Oh. Google took. There's no obvious explicit demand. I will buy it. A lot of people will buy it. But yeah, I think that this, I don't think that you can actually get that uses the XLA deep learning compiler. Yeah. All right. Let's understand how Google's memory works. 4-dimensional tensor DMA, that's great. Triple strided. Oh, well, this is actually really easy to write in a DMA engine. I want the strides to apply instantly to my hyper-fast SRAM. They're doing 512 bits. So I wanted my memory access size to be 19, but okay. What we might have to do is force the stride size to be 1 on one of the dimensions, which sucks, but then like we get rid of that squared factor, and then it all becomes like, okay, instead of asking for a 1024 port SRAM, we're asking for 32 port SRAM, and that's much more doable. Yeah, I mean, everyone complains about this, right? And like, you know, no one just does it, right? And is comma not proof? Like, it's because these companies, it's the same reason that there's no self-driving cars, right? You get one company that like happens to do it, like Tesla, and then there's like us, like, and it wasn't that hard. Like, comma and openpilot weren't that hard. It really does show that it's not a. There's a serious cultural dysfunction in all of these companies. Nobody should ever listen to investors, you know, because investors are not aligned with value creation. Investors do not want you to do anything, because if you do something, people might evaluate it. If you don't do anything, you can hype it up and dump the bags for more money. Right? So I think that might be the problem with all these AI chip companies, right? What do? if you've raised $600 million, where do you go from there? It's the same problem. I don't know. I don't think I have the patience to do it again. You know, I really don't want to start the company. Like, I've been talking with this guy. I want him to start the company. It's apparent he's not going to start a company. You know, because no, there's no issue. Like, you can just do this, but you have to do it. And like, self-driving cars, I had this advantage where it was very clear to me that everyone was a complete moron. Like, that whole space is full of actual complete morons. These people aren't morons. Like, these people are a little misguided, but my main problem is not, like, I would just love some TPU v4s. Right? I could probably write something good that uses them if they, like, stuck one on a PCIe card. Right? Like, I could use these things and make them work with TinyGrad and make them work with PyTorch without going through 7 layers of transpilation. If I can reverse engineer the Apple neural engine, you know, the rest are easier. You know, it's not like Grok's easy to make fun of for their VLIW. The TPU has much more sane VLIW instructions. Yeah, 322-bit. Does it divide by 8? No, it doesn't. So, you know, you when you compare the like the Grok instructions are 57 times larger than the Google TPU instruction. 322 is not too insane. We'll change it to, they look okay. We'll change it to okay. So yes, it is enough performance. So K. Beckman, yeah, you're right about the VRAMs, and so I'm synthesizing that, and I have this is a VRAM up here. Look, we can prototype this. We can make this all work. The problem is this little mux. To build this fully muxed thing. This one we can build fully muxed because it's small. I'm wondering if we can build the final one fully muxed. But yeah, probably. We gotta put subscriber only mode back on. We got some dumb shit. What? I need to learn a pile of EE stuff. Let's go, bro. Let's go. Wait, no, turn it off. Turn it off. Fargio, let's go. What don't I know? Let's go. Explain to me what I don't know. We'll give him a minute. We'll give him a minute, and then we'll put subscriber only mode back on, so that the, like, I'm a moron and I thought everyone else was morons, but I guess they're not. Or the just use homomorphic encryption, you know? Okay. What? So signal integrity, metastability, transmission lines, propagation delays. Yo, I'm not trying to write EDA tools, man. Like, there's tools that will do all of this for you. There's tools that'll do all this layout. You have to pay attention to a few things that are difficult, but like, what do you mean you can't just shove in a 600 megahertz clock? I do the tool tells me what my propagation delays are. Here, I'll show you. Right? And like, there's these same tools that you basically use to synthesize for FPGAs that also work for, all right, so here we go, compile, right? So this is gonna compile and actually run it in the FPGA. And if you can run it in the FPGA, you can run it in an ASIC, you know? What is an FPGA? It's just an ASIC. I can rip out all the configuration shit if I really wanted to, right? So like, if you make it work in an FPGA, at a certain clock speed, you made it work in hardware, right? So like you tell me, oh, you can't take software style approaches to this. Yeah, I fucking can, right? Like watch, I'm doing it, right? Like we out here. All right, let's go back to subscriber only mode. How do you learn Vim? You don't. You use Notepad. I don't think most chips are auto laid out at large scale. So what they have is macros for a lot of it. Like for like your SRAMs, you're gonna have macros. I don't know. I mean, yeah, you can auto route it. The same reason you don't auto route PCBs, but there's turnkey companies that I can just send it to and they'll do the layout for me. I'm really not worried about layout. So no, I mean, yes, there are hardware considerations, but like really, Verilog is a programming language. It's not. You can think of it the same way. You just have to like, you know, you guys ever code in Prolog, man? Like I coded in Prolog once. Can I buy a Huawei Ascends? Maybe the Chinese, man. Maybe our culture and society are too fucked to build anything anymore. And maybe I can buy Huawei Ascend 910s. Please, will China sell us thing? I don't know, FP16 though. That's the other problem with all these chips. They have like FP16, which isn't good. The only chip that does this right is Nvidia's. Gee, look, it's routing my chip right now. I'm not thrilled that that got slower. All right, so are there ways to like view? I kind of want to like view where all my LUTs are and shit. Intel computer, yeah. So yeah, we have, I did the math on how much bandwidth we actually have, and there's enough bandwidth. This mux is annoying, and I have no idea if I can actually build this mux at scale. I don't know, maybe I can. You can open the netlist Verilog in Vivado. Well, I don't have Vivado. I haven't actually got anything to route since 9:45 this morning. This is unrouted. Whoa, that's so cool. It shows me like what. How trivial is 12 nanometer manufacturing? I hear it's pretty turnkey now. Let's take a look at our so that's synthesize. View output of Yosys. So cool. Systolic array. What does that mean? Oh yeah, God, this looks awful. Yeah. I saw this, how Google was doing like the shifts and stuff. Yeah, exactly. Like this is what I mean. These things are impossible to program for. Nobody built like a sane programming model because I've already written the programming model. I started with the programming model, and now I'm upset that I can't get my SRAMs to fully stride. But like, you know, I think we can make the SRAMs fully stride. Wow, routing's taking a long time. Oh no, we're up to 1002 frames. Routing's finished. Big file. Okay. View Yosis JSON output. Did I already Google that? I feel like I did. Yosis JS. Oh. Mint. Draw an SVG schematic from a netlist. Oh my god, I can tell already that it's going to be huge. Wow. What does FASM to frames do? All right. Netlist SVG, add a sock JSON, temp.jump.svg. Wow, whatever FASM to frames is doing, it's using big CPU. Maybe, why is it making my computer so? Oh, finished. Oh, we routed it. Okay, well, that's great. Didn't work. Maybe routed? No, useless. Changes a bit, which broke. Oh. I have to use the compat int option of the write JSON. Compat int, no good. Oh, we have to write, oh, just write JSON compat int. Oh. Well, you know, don't you all like how we learn on this stream, like we learn together about like what these tools actually are? We've learned so much about FPGAs. You can use the dot command in Yosis to plot a graph, but it'll be huge. Yeah, great. I mean, I feel like this SVG is going to be huge too. Oh, what's that? NextPinter has a graphical user interface? Oh, I feel like I didn't compile that though. Found an out of range parameter. Well, that's great. It works with netlist SVG. It doesn't even work with netlist SVG. This is terrible. Okay. Apparently NextPinter, I can do... has a GUI? But I feel like I didn't build the GUI, and I feel like this was a while ago, and it's going to be hopeless to try to bring this stuff back. Fun, FPGA, next pinner Xilinx, next pinner Xilinx. Whoa. Oh, I can set the target frequency. I set 12 megahertz by default. That's shitty. Yeah, but I definitely built this without the build GUI. Oh, maybe I did build a GUI. You guys saw the last GUI. How do I get the GUI? CMake cache? Let's take a look. Oh, build GUI, no. Build Python integration, no. Oh yeah, I must have done a lot of this stuff. Did I document this anywhere? Probably not. Tiny grad, FPGA. Maybe I documented a little. Here we go. Oh, perfect. All right, who thinks we can get the GUI to build? Boost. No boost. Complains about boost too. So maybe it's fine. Okay, never mind, it does nothing. No boost. Maybe there's cool upgrades. Could not find Python libs. You don't have Qt5 now. Found boost. Find Qt5 brew install. This has always been. Qt5 dir. Do I have Qt5? I do. Try dqt5 dir. Okay. All right, now we have a problem of no boost Python. Oh, this is some Yosis crap. Brew install boost Python 3. Think it's gonna work? Yeah. I fixed Qt5, now it's boost. Now I need boost. I don't know. This is kind of a tangent. There's gotta be some other way. Should we just write our own visualizer for these JSONs? I think we'll learn more doing that. All right, well, this is working anyway, so let's go. We'll add that to tiny grad FPGA if it works. If you only want to know which slices are used, yeah, I want to know a little bit more than that. I want to just see like how these multiplexers are being laid out and if they're being laid out stupidly or not. So cool that all this stuff's open source. We could also try, yeah, manually looking and seeing, well, let's rebuild this so we have the problems later. Oh no! All that and it didn't work. It failed to link to Python. No, that stuff's here. We just need to link to it. Can I say something? Oh, actually, I was just running make, right? Can I say something like C flags equals -L Python 3 times? No. No, I don't think that's the problem. I mean, the GUI might not work, but that's certainly not what's happening here. This is just, it's not linking. Will I hire people for Cherry Computer? Yeah, maybe. I told you how to get hired. But if you're only doing it for a job, just like, you know, if you're not, it's going to be even more extreme than comma in that fact. Like, this is not, Bunny once talked about this. He's like, you only do this because you love it, man. You know, people who are like, well, I'm going to send my resume to 10 companies and look for a job. Like, I don't want you working, you know, at Cherry. Like, this, who wants to work with people like that, you know? It's like, we're trying to, like, build something cool. It's a lot of, you know, it's just a lot, like, I don't want to start the company, right? It's so much effort, and it's so painful to, like, you know, you get, like, an email, hello, hiring manager. And you're like, George, well, you know, you could hire people to deal with that for you. Yeah, you see the problem? If you're a little slow, the problem is you got to hire those people, right? And you got to manage them. It's the same thing, right? I don't care if people are fucking obedient. Like, you got through school, man. Yeah, that's why, like, school teaches all the wrong stuff. The integrated show command of Yosis. Is this the dot? All right. Well, let's try that. Okay, we can try this. Let's see. Can I read JSON? Read JSON. Is this gonna work? Oh, okay, cool. High level, no, this isn't what I want. How do I do show? Show? Oh, I need X dot. Okay. Cool, I just need X dot. Brew install X dot? I don't need all of Xorg then. Or should just anything that loads a dot should work. There should be a file called Yosis show, right? Oh, that's a big dot file. X dot. No bottle available. I just want to show after, you mean after routing? No, that's already after synth. Show, no, not a dot file, graph dot file. X dot, brew install graph is, and then, do I have dot? I do have dot, okay, good. Okay, dot, Yosis show dot, tping, out dot, temp dot ping. Oh yeah, this is gonna take 7 years. Let's go. I should have a formula for X dot and brew. I do. I have to build it from source. We can try it. Gucci game. Every time I see ghcr.io, I think I'm installing some Haskell crap. It worked fine every time without a crash. Uh-oh. Yeah, this isn't really working now, is it? Just want to look at this in Python, like load this JSON. Great, we're upgrading FFmpeg now. We're running the router. No, I killed the router, didn't I? Did I kill the router? I forgot. my computer's getting slow. Slow. It's going slow. It's going slow. Why is it slow? All right, we're going to Control-C that. How many Chromes do I have open? This computer needs more RAM. B-brain flops. Yeah. Who remembers that? All right, too many Chromes. Gotta kill some Chromes. That didn't finish. Oh my god. Okay, wait, do we have XDOT now? No, but we upgraded FFmpeg. Great. Oh no, we might have XDOT. Okay, let's just try again. Show. Oh, now it's running in the background. Oh, that's great. Gotta love these hardware people. Yes, secretly use my CPU and don't tell me about it. That's exactly what I want. All right, let's just write some Python. Call it Viz. Not Biz, Biz for losers. Viz, that's right. All right, open /. Oh, it's like running dot in the background. I don't like this. Kill all dot. No more dot. Oh, dot was upset that I killed it and it showed up over there. It's like, okay, it came up with a thing and it said okay, and it's like, I understand you're killing me because there we go, great. Pylab inline import JSON. JSON dot loads. Load open. Out of stock JSON. Dat. I don't even know, like, what is this? Well, there's no 0 in there. Is it a dictionary? Okay, we have creator and modules. Am I creator? I'm not creator. Yosis is creator. Good point. All right, let's look at all our modules. We have a lot of good modules in here. What's an ABC9? Ooh, I didn't know Xilinx came with mults. We have a mult? Oh, it's an embedded multiplier block. Cool. Good thing I didn't use the DSP blocks. Those apparently don't work. Okay. Let's go through the modules. And let's print... let's print K for now. Okay. So these are all the modules. Where are LUTs? Oh, look, I love LUTs, man. All right, how about LUT 6s? Well, you know what? Let's look at the BRAMs. I know I have BRAMs. It's this one? Attributes. Port cells, net names. Okay, do I want to look at the routed one? Maybe I want to look at the routed one. If we don't look at, well, no, I shouldn't need the routed one. Net names? ABP. I'm not using any O cerdesses, am I? Oh, Oh my god, but they still have stuff. Cells extra. Looks kind of cool. You want to just look at it? What is this, like the GCC of created by Cells Extra for Xilinx modules? Okay, who actually knows how to look at these things? I have an idea. Let's print length repr dat module subkeys. Let's see where actually all this like 30 megs of JSON is. No, not, oops, I forgot a K. No, ugh, stop. That. Okay. HBM? I definitely don't have an HBM. You mean like RAM's HBM? Top. Oh, there's a lot of stuff in top. Am I routing done yet? Yeah, routing's done. So we can look at the routed one. I don't know if it's different. Oh, it only has top. Okay, maybe it got rid of all the other crap. Okay, well, that kind of makes sense. Oh, does anyone remember how to build the chipdb binary? I documented it. It's in the TinyCode repo. Vim open editing that? Do I have another window? Oh, here we go, I do. Still broken on OS X. Tell me, is the GUI nice? Is it worth trying to get this GUI working? Or should we keep playing with our own? Oh, that was a mistake. Okay. Cells? Oh, cool. Oh, so these are all the things. FPGAs are so cool, man. Let's figure out where those LUTs actually are. Break. Clock inverted. Construct parent. Oh, maybe just K actually. Yeah, okay. I'm trying to figure out what's using all my LUTs. So TC dot, why did I name things better? Risk stride Y, ABC ops reintegrate, Eiger. These are stupid names. What's Eiger? It's part of Yosas? This is before it's routed. This is kind of nice. TCRI. Oh, okay. So RI is the things that I'm playing with. All right, well, should we give them slightly better names so they stop showing up stupidly? I'm gonna have to wait for it to resynthesize. So in my CPU, I called RI is the RISC engine, RISC with a K. All right, we need to give this a better name. It's a pretty stupid name. But yeah, R is what I call DRAM. Well, we gave all these things stupid names. R. All right, the regs are the regs in the RISC. So this is my implementation of the RISC accelerator. We need to give it a better name. We'll just call it Cherry. We'll call it the Cherry instructions. I'll do all that renaming off stream because it's kind of boring to rename things on stream. But yeah, we'll call this the Cherry. You got to put a cherry in your RISC. All right. What's an FDRE? Yo, Xilinx has great documentation. I love Xilinx. These guys are bros. Xilinx bros. It's a D flip-flop with clock enable and synchronous reset. Just want to learn about LUTs. They have LUTs in here? Oh, we can look at a LUT. Oh, cool, man. We can build our own FPGA out of this. Yo, we could build an actual FPGA simulator that operates on the routed thing. I don't know if anyone's ever done that. It sounds kind of fun. Advanced mix mode clock manager. Look at this stuff. All right. Do I use any multiplexers? Kind of sucks that they don't have good names. Well, not Eiger. What is the Eiger? The current design to an Eiger file. Well, that's great. Oh. Something's wasting all my LUTs stupidly, though. Gen block 2. Oh, gen block 2 from generate. I see. Yeah, it's all these Eigers that are bad, though. And they do show you, so here, we can go to where I routed it and we can take a look at, yeah, it shows me the usage. So we're at 14% usage of the FPGA. And like, I don't know if that's good or that's bad. I got it down by, and this is my simulator for the memory. You just do iVerilog, but instead of this, you run risc test bench. And that's like simulating a load for the memory. These are all the computed addresses. I just wish I knew which LUTs were attributed to which line is really what I want to know. Because we have all these LUTs and I want to know like which code I wrote that like ends up turning into lots of crap. Maybe construct parent? Oh, source. Oh, that's pretty cool. The type, no, not type, sorry. Parameters source. Parameters? Where's that? Oh, it's an attribute. It's not a parameter, obviously. That makes a lot more sense. Actually does kind of make sense. I shouldn't make fun of it. Okay, well, LUT map. Oh, are all the sources just LUT map? Oh, that's lame. Oh, this one's top risc CPU arith map. What's an arith map? Whoa. Do you use loops in your code? I do use up loops in my code, yeah. Yeah, but I need loops. I'm as upset about the loops as you, but I'll show you where my stupid loops are. Right, so it's actually even worse than loops. I have nested loops. So like here, I have this loop nested inside this loop. This whole thing's a priority encoder, and then this is a multiplexer. I wrote the multiplexer by hand instead of using the loop. But yeah, it's n squared, I know. And like it might already be efficient and I might just be chasing non-real gains. But that doesn't mean I'm not, you know, very upset about how much of the FPGA it uses to do muxes. I mean, I guess this is like a fundamental, like there's just no way to do this better. Here we go. All those LUTs come from line 88. What's on line 88? Oh, the adders compare. All right, well, that's kind of nice. What did I just do? Okay, what makes for a better stream? I mean, you guys can watch me struggle with this for a while. But let's look at what other people are doing for their memory. We still didn't get to the bottom of what Google's doing, but Google needs a lot less memory bandwidth than I do because they're only loading the outside of the array and not the inside of the array. They look okay. I like that. They look okay. Architectural memories are VPU and VMem. CMem. How do I load from the VMem? This is the problem. You start adding all these memories and then you spend all your time figuring out how to change between your memories. All right, can we turn off subscribers only, and can you all be on topic? And if we want to be off topic, then you know, leave. The branch predictor, bro, it's Verilog. I don't even know if you're trolling. How can I be on topic if I don't even know what the topic is? You cannot say anything until you figure it out. New here, what are you building? This is a problem. You know, when we have like 300-person streams, it works much better. It's when we get these like 750 people that it gets really bad. No, I know it doesn't matter the percent, but I don't want to use a lot of my FPGA, and if I'm using a lot of my FPGA, it means I'm not you know, building efficient stuff. It means I'm going to have to use a lot of transistors. There might just not be a way to make this more efficient. Fundamentally, what I'm asking to do is I have like 1,000 RAMs and 1,000 registers, and I want to, you know, be able to draw any line between them. The problem, of course, with drawing any line between them is there's a million possible lines in your little bipartite graph there, right? There's a million edges in a fully connected bipartite graph with two sides of going all the way through to the foundry. Yeah, tell me that you love me is the reason it's sub-only mode again. You're right. The tools make loads of optimizations. Yeah, no, I understand that. I mean, I have found, by the way, I've written this code like a bunch of different ways, and you get huge different amounts of. It's really just that I don't want to be asking the tools for the wrong thing. Like here, I'm technically asking the tools for the wrong thing. So this has to be a priority encoder, but for this, I can just use the same sort of multiplexer I'm using down here. Like this multiplexer saved me 3% of my FPGA. Switching to this from that saved 3% of my FPGA. Yeah, and the router gets more and more suboptimal. I mean, the router just takes longer, and I'm really impatient when I'm compiling these things. This was a cool thing that I read earlier. But I mean, I think the better question is like, do we really need the fully strided memory? If we only needed to stride on the other array, it's much easier. It is pretty much an explicit mux though, and it's really big. For these ones, I'm intentionally using equals because look what I'm doing. I'm using this for loop to build up basically a big OR of all of these outs masked by lmask. No, I just think that, like, fundamentally, what I'm asking for is going to require millions of transistors. And then there's a question of, is that really what you need? Because if we went only 32 wide instead of 1024 wide, like, look at all those transistors we saved. So how about the Huawei Ascend? Do we have any more information on this? What are they using? Or should we dive into Nvidia's memory model? And Nvidia has published, okay, Nvidia Tensor Cores Assembly. Actually, someone linked to a good thing. Tensor cores are very fast. So fast, in fact, that they're idle most of the time, waiting for memory to arrive from global memory. For example, during BERT large training, which uses huge matrices, the larger the better for tensor cores. Yeah. We'll add that to the blog post. And for other GPU attributes, shared memory, L1 cache, and the amount of registers used are all related. Exploit the memory hierarchy of a GPU. The faster the memory is, the smaller it is. Such. Tile size. For matrix A, we have 33. For B, we have that many. Oh yeah, you guys know about 128 and why that's true. Okay, well, so my register size is for 32 by 32 by 19. Or actually, let's just say they're one, yeah. In the past, Nvidia sneaked unannounced performance degradations into the GPUs. So here's a whole other project. Here's a whole other project. If you and like apparently it's really hard to do, but if you could do it, why doesn't someone just write open source like so Novu did it, but write an open source CUDA driver for Nvidia. Like, how much are they really nerfing these GPUs? This still doesn't fix really the problem of chip availability, though. But I mean, the chips are kind of available. I don't know. Like at least you're more open source. Doesn't it break the terms of service to write a new driver? No. I could definitely write my own driver for Nvidia. Breaking the memory wall for an AI chip with a new dimension. Near memory computing architecture? What's near memory? Can't believe I'm even going to pirate your paper. If you guys don't know about Sci-Hub, Sci-Hub's great. Yeah, I know there's keys, and the keys don't let you set the clock right. Yeah, I read about this. We choose to use DRAM over SRAM. The DRAM units are pooled together. The feature data is broadcast to all vector processing units. Each VPU computes and generates output channels independently from other cores. The results are sent back to a central memory pool. Then VPU performs all the operations necessary. I mean, this is an interesting idea, right? If you really wanted to build a chip that would blow everything out of the water, ditch your onboard SRAM. If you could figure out how to get your DRAMs to look like SRAMs, like what if the only SRAM on the chip was actually the registers? And you have a whole bunch of registers, but they're all registers. Like ditch this 20 meg SRAM. If I'm already building this super complicated multiplexer, why not build it in front of the DRAM? So how many DRAM? Yeah, I mean this kind of thing. When can you buy it? I'm not really starting another company. You know my advice, don't start a company. But yeah, what if you didn't use any SRAM? Okay, let's look at the DRAM interface on a GPU. Nvidia chips. There's like one Wikipedia page I always go to for this. This one. All right, so the bus width is 384 bits. It's actually not that many bits. It won't even feed one of my what's a 6T SRAM? What's a 6T SRAM? What's a 6T? This is just like a normal SRAM. We don't have wide enough buses. So like my bus width on the so if we're using the, hang on, let me just load up my Python simulator for this. So if we're using this, we have 2048 BRAMs, each with 18-bit. Our bus width is 2 orders of magnitude higher than Nvidia's, and that's the problem. Right, like that's our SRAM bus width, which is insane. But the only reason they're capable of getting any bandwidth out of these things is because it's like GDDR6, which is like, oh, we send 4, things per potential solution. What do we got? No. No. Anybody who's trying to do AI research at the same time they're doing computer architecture is seriously making a mistake, right? You see a whole bunch of these startups doing it. They're like, oh, sparsity is going to be the new thing. Oh, you're having in-sort algorithms. This was the tensor video, and like, why are you doing research? Why don't you just beat MLPerf? How much tensor compute these things have? So much. Huge tensor compute, if you can use it. Yeah, so the bus widths are too small. Like I want a bus width like that. Guys, on topic, or we go back subscriber only. And if it's one person off topic, is banned. No, don't. Oh my God, binarized nets. Like, okay, the reason. The goal of good hardware is to make the software people happy and like the hardware. And then the software people will pay you back tenfold with great software. If you piss the software people off and force them to write things like, net quantization and gradient scaling, and then the software people will hate you and not write good things for your hardware. I don't know. Does anyone know if this multiplexer is like, because fundamentally I need this multiplexer if I want to support any stride. If I don't want to support any stride, I can divide that by 32. All right. Subscriber only. Sorry, the guy about startup culture is the reason we went subscriber only. Yeah, I don't think we need 6T. I think normal SRAMs are fine. It's just like, is this too big of a switching bus? Let's understand caches, because what this really looks like, cache associativity. Yeah. This is a 4-way associative cache, and that's the MUX. That's a lot of comparators. Yeah. See, they're talking about like 8-to-1 multiplexers. Nobody's talking about 1024-to-1 multiplexers. No, I'm not actually specifying a MUX explicitly. I'm doing a pretty minimal thing. How can you help improve TinyGrad? Well, you can submit pull requests to TinyGrad. That's how you can start. Set associative cache, 2 or 4 frames per line, blah, blah, blah. Because we have this big comparator. We didn't exactly use a comparator, I used a mask, but it is that same comparator. Oh. No, it's not actually that. Yeah, what book? Yeah, what the book suggestions? What do you got? No index is needed. A fully associative cache of M-block is an M-way set associative cache. Largest fully associative cache ever built. The other thing that we could consider is we could make the whole... I'm not happy about this. But if we got rid of... If we only made the stride possible in one dimension, then like things become a lot easier. We have much wider BRAMs to get the same amount of memory. That's true, right? Oh, I think we'd win both ways with that. Right? I think what we could effectively do is to get the same amount of memory, we could use the full width BRAM. The data still has to come from DRAM. Anything that uses faster than DRAM can deliver will be bottlenecked by DRAM. Yeah. So the whole point of the way that we're not going to be bottlenecked by DRAM is that matrices have n squared data accesses but n cubed compute. Yeah, I think that would actually really... God, I like my stride though. I'm upset, but we're gonna have to change the, I don't think you can make the stride. 0 stride is fine. XS is usually pretty small. So I'll just be able to ignore them. Yeah, this fully striding thing is a pipe dream. All right, then that means we need a permute engine. Becomes less of a joy to program if we get rid of my 2 strides. Computing the address is easy. The DRAMs themselves are easy. The problem is the thing that can mux them. So, I mean, maybe there's some way to be clever. Like, they can't end up anywhere, is the problem. Because if they end up anywhere, you need this fully associative thing. I believe that we could get something that's fully associative for 32. Right? Because, I mean, even this little FPGA can synthesize something that's 16 by 32. So I think we'll be able to synthesize something that's like 32 by 64 or something. But we're never going to be able to synthesize something that's, you know, and actually this would become 4 by 8 if we switched it. This is the book. By Nvidia chief scientist. Oh, okay. So here's, I think, maybe what we should focus on then. And I think this is a good place. I mean, there's a reason it's called the memory struggle session. I think this might be a good place to end the stream. Unless there's something I am not understanding about how you can build this easily, there's going to be no way to do a full fetch across all of them. We're going to be able to have a permute engine that can do a few cute permutations. Maybe we can figure out what the Google one can do. But my dream of a magical, fully associative thing is Not gonna happen. So we'd read in like the whole row. I will definitely check the book out. You guys don't just want to watch me read on stream though, do you? This looks good. Yeah, this looks really good actually. Why does it have bad ratings? Book packaging is bad, I see. I have an idea that my PDF will be packaged pretty well. Oh my god, they don't have a table of contents? I hate that. My book that I stole doesn't have a table of contents, and I'm upset about this. It says draft edition? Oh yeah, let's get not draft edition. Still no. It was even worse. Someone like scanned it. Someone scanned the book. It is better formatted, but scrolling's not working well. Yo, we're live streaming crime. It can't be illegal to go on Google and click a link. I didn't know it was illegal. I think Google's liable. LibGen? I love LibGen. Man, we're in a golden age for piracy, everybody. We're in a golden age for piracy. Draft edition. First edition. Oh, that's a big PDF. Let's find the small PDF. Which is the good one? You say this is the good one? I think this is that same. It's gonna be scanned and stuff. Get. Oh, I love get. No, what do you mean? I own this book. It's in the other room. You know what? You know what I overpaid for your 3090s? Yeah, I think this is going to be the same. I should remember to use libgen more. 28? Where'd you find 28? What's 28? Who would want to use VHDL? Oh, they wrote a VHDL edition of the book. I see. Why'd they write a VHDL edition afterward? I mean, it's kind of nice. You're right, this is the best one. Oh, this is way the best one. Thanks, libgen. I mean, it is a scanned copy of the book, but... Oh, this is nice. All of Europe uses VHDL? Why? Sequential logic. System. What's system level design? Oh, it's like understanding states and stuff. These are all cool ways to think about things. Yeah, I know, but I don't want VHDL. I'd rather a scanned book that's in Verilog so I can read it. The digital abstraction. I mean, okay, so there probably are like better ways to build the thing that I want. Memory systems. Memory. DRAM. When we need a memory, larger or wider than we can build, with bit slicing, we divide the primitives across bits. With banking, they're divided across the address space. Yeah, but look at all that bandwidth I'm wasting. Oh. That's an interesting point, though. I don't actually need ORs. I need latches. I guess that's what I've built, right? Is that what this is? I tried to build this with that. Did I check the Xilinx documentation? Which is this? What? No. I'm not using any of this. I didn't know Xilinx had an AI engine. What's in their AI engine? I mean, this is kind of cool, but two load units. What's a load unit? You better copy the book. Yeah, VHDL. Ugh. Out. So like, yeah, they just like took all these latches and like stuck them together. I guess there's implied ORs there. Oh no, that's not even an OR. That's a concat. But that's an OR. Yo, VHDL's not good. I used to code in VHDL and I switched to Verilog. The PDF quality means VHDL's better. That's funny. In real memory systems, Oranges with full associativity. Yeah, so see, like, I mean, ideally you want to put them together in a grid like this, where you concatenate along the bits. Yeah, that's like really nice, right? Like, think about it. But so if we made like each line only have one VRAM that could go to each line. Okay, can I get a online paint? All right, so basically we have a matrix, right? Let's make it 4 by 4. Those are tiny cells. Okay. So right now, I have this 4 by 4 matrix, and the code that I've actually written over here synthesizes 32 VRAMs, right? So I have 32 VRAMs. We'll just draw 2 VRAMs for reference over here, right? Now, the problem is that there's a way for every one of these VRAMs to get to every single thing. So like there's a line here, there's a line here. Let's use a different color for these lines. Let's make these lines red. All right, there's like a line here, a line here, a line here, a line here. And as you can see, by just watching for a little bit, I'm drawing a shit ton of lines, right? Because, you know, this VRAM also needs a line to every single thing. Right, and then someone's got to make all these lines. Who's going to make all these lines? Who's going to pay for all these Gatorades, you know? So, guys, I'm not here to argue over which one's better. I used VHDL in the past. I found it more confusing. I don't think it really matters. It doesn't matter whether I wrote this in VHDL or Verilog. It's still... Okay. Well, it won't let me undo anymore, so we have to figure out how to use the eraser in this thing. Is this an eraser? That's not an eraser. Oh, that's an eraser. It has an eraser shape. Okay, good. All right, good. So if what we did instead was only connected these things, like the blue ones, to here, and then we make more VRAMs, it's like, okay, so the red one can only go to these, right? No, it's not red. You see how many less lines we're drawing? It's almost so few lines that I'm willing to draw all of them by hand. Almost. Right? And then the B's, the blues can only go here, and the, you know, greens can go here. The problem is, if you want to get a red thing into a green thing, you got to do a lot of stupid software, right? I mean, this is like, you know, the separate but equal approach, right? It's like, you know, we put the yellows here, the greens here, the blues here, and the reds here. And then I guess we could have like internal We could have like internal matrix permutes, which go like this. But now we gotta write complicated software to do shit like that, and that requires lots of instructions. You see the problem? Alright, let's let the non-subscribers talk a little and see if they're going to pay attention. I drew a simple picture for you guys. I drew pictures. I'm very upset about this. To Pinky. Alright, we could also make like the teal, which does the matrix transpose. Like that one goes here. Like this one goes here, and they swap, right? So we can make like the teal path. We could make the purple path. Yeah. Right. This is a lot easier to write, But then we don't get fully strided. It's the twister strategy. Alright, we'll sell my art as an NFT to fund Cherry. I was just so much happier drawing all that because, like, imagine I had to draw all the red lines to there. Like, you can just see why it's terrible. How come either tools can't take my diagram and translate it into an ASIC one of these days? One of these days. Alright, so like, yeah, we have this like matrix array, and I guess we could like write those instructions. Oh, I mean, that does seem more Risk-like, don't you think? I mean, this is all built. Yeah, no, the fully associative thing is beautiful. Use AND blocks instead of the 4x4 block, with each AND representing one square and having 4 wires which represent the incoming data. Some kind of I did implement a small unit. I implemented this, but fully associative, and it used way too much of my FPGA. All right. You know what? That's a good way. That's a good thing to try. Okay. We know how much of the FPGA this uses with the fully connected ones. The fully connected ones use 14% of the FPGA. All right, let's do the non, and then it gets really bad when you want to make it bigger. Like, it's not that much of a problem yet because 16 is actually a doable thing. But okay. So let's just quickly try. If we were to double this, these would go to 68. We would get rid of all the Y. We would only have, no, well, actually we'd get rid of the X, and we'd only have stride Y. We'll just take one of these sizes out of here. And then actually count becomes way less. I mean, this isn't that good of an exercise because, like, It's actually a better exercise than saying like, yeah. Oh, this should actually be 67, right? And then this makes the BRAMs like big BRAMs. That just links up. That would make this 4x 18K BRAMs instead. Right, we get rid of stride X. We'd have this logic only for stride Y. Twitter doesn't work. Oh, Google does have a TPU v5. Oh, this is scary, guys. You guys heard of the singularity? Like, this is the singularity, you know? When AI is using AI to generate AI. Sci-Hub, it's about as reliable as Twitter. Try zlib? What's zlib? I mean, it's compression, but... DOI, not title, and Sci-Hub. Oh, okay. What's zlib.org? I've never heard of this. I love learning about new websites to legally access free material. What is this? Deep learning. The nature of space and time. Facebook.com. What is this? I love Z Library. This one I'm sure is just a way to get. I heard about this too. Or not. Nature. Oh, it's in PubMed. Oh. Maybe I can search by the PMID? PMID? Wow, this is hard to pirate. Open tweet, go to person page, click the Twitter link from Nature. Didn't work. Oh, krasne przewiedzenia. Open access link. Oh, here we go. Link to the non-paywalled text. Great. I'm gonna have this link to the blog. Using. Huh. I mean, this is a cool idea. Has anybody tried to write this in these FPGA routers? Like, can we rewrite next pointer Xilinx but using ML? Read the last tweet in the thread of Jan LeCun. I mean, is it real? It's probably real. Oh, Jan LeCun says it's a scam? I mean, it might be a scam for now, but it won't be long before it's not, right? Like, think about what these algorithms are. You'll do a much better job with something. I'm still waiting for the, really, I'm waiting for the neural network sat solvers. Like, has anyone done neural network sat solvers yet? Not good. Oh, these are all the same stuff. Yeah, like these papers are old and they're not very good. Because it really is just that. Oh, we should add a little note about the TPU V5, which I likely also won't be able to buy. So SAT is discrete, yes, and you probably want the architecture to look something similar to like AlphaGo, right? Like you have this search component which shouldn't exist inside your neural net, but then you want to figure out like which of the parts of the tree to expand, and that you can do probably a good job with your neural net. If I don't get my strides, then we have to be more careful. If I don't have strides, we have to be a lot more careful in the software. If I only have one dimension of strides. We need at least one dimension. Oh, strides are a scam. They're not. Didn't you see my picture? Alright, so like this one, H times W, where I'm loading in the channels. Like that would just take much longer to load. Or we'd have to write our conv in a different way. These ones have 1 in the stride, so they would be okay. 0 in the stride would be okay. There's nothing we can do about XS in the stride. Can maybe mask? We probably would want to mask them. See a dark light bulb. Actually doesn't matter. We're doing Molax, so it's not like it matters. Unstrided 1x1 columns are matmols. So they actually have stride 1. All right, we have to write the backward pass before we can say anything about whether we really need these strides or not. All right, somebody write the convolution backward pass in risc-v. So like use these risc-v operations in the backward pass, similar to how I did it for the forward pass. And then we'll see whether we really need the strides or not. If we don't, I think then all the details of the chip are figured out. We need a permute engine. Cool. What else we got? We have anything else to discuss? I think we've come to a sad truth on the memory architecture, and it's we're not going to get this magical thing that I want without spending a lot of power on it. Because yeah, I mean, yeah, 1024 is insane, but things on the order of like 32 are more reasonable. prefetching. Yeah, I know about prefetching. It's not like, I mean, we know everything. And now I get, and this is why everybody falls for this, like, okay, we're going to build something that like carefully maps out all the memory accesses before we do them, but count will get divided by size. You'll lose, I mean, count is effectively size times size. So it's size to the fourth and it'll become size squared. Great paper about use in AI chips. Process in memory technology, yeah. Am I gonna do internships for this? Who's writing your, who's doing your government, you know, that I have to pay your taxes paper? Who's doing that? You want an internship? It's free. You got a free internship right now. Go contribute to TinyGrad. Go write pull requests. I show you, we got to implement this stuff in the instructions. Add reduce ops to risk and fully support forward pass. Yeah. Unpaid internship. Congratulations. It's yours. You got an unpaid internship right now. Congratulations. You're an intern for Cherry Computer. Put it on your LinkedIn. But you got to do, you got to submit pull requests first. You submit pull requests. You put on your LinkedIn that you're an intern for Cherry Computer. Yeah, there we go. No, you don't work for me. You work for nature. You work for GitHub. I'm not going to, you know, what do you expect working for me is? See, you get some people who like want to like, oh, come work at Comma for free. And then you find out that they don't actually want to work. They want to be educated. And I think that they misunderstand the way that that works because education's actually super expensive. Nope. If you submit a pull request for grammar, you can't write that you're an intern. You'll have to write that you're a low quality technical writer. Yes, you can have that title. No, the only reason education's not expensive in Europe is because, well, actually it is expensive. You're just not paying for it. If you want to educate yourself, it's free. You want somebody else to educate you. Did you study CS? Timeout. It's free. You only pay 50% of your salary every year, bro. That's true. If I don't get my fully strided memory, I'm less happy. Yeah, but I mean that actually, this book was great, and like this picture shows you why you can't do it, right? Because if you're trying to go fully strided, what you're doing is you're taking all your SRAMs and you're stacking them in a big line. Right? And then what you don't see is all these OR gates that you then need as well. Yeah, all right. We're going to have to start looking at memory access patterns. Fully strided seems to be overly complex for the perks. Yeah, but then like, so what do I do about like this? Well, okay. I could have the matmul instruction taken a mask. So at least, no, but it's a lot of circuitry in the ASIC. It is. You can't, if you could build what I'm asking for, caches would be like 1024 way associative. No, I understand that an OR gate is, oh, it's 4 CMOS? I thought it was 6, but still. I shouldn't put this here, I should put this in. Add masks to matmul instruction. That's actually really easy to do. So we can like mask things off that we don't need. We understand also now what we can build in hardware and what we can't. That was my big question, was around the strided memory. So I think the next step in all this stuff, with mask you want to implement stride greater than 1 is mask stride equals 1. Yeah. Of course we don't get to use all the compute, if we're applying a mask. I know, I'm pushing to software. I'm not happy about this. See why I'm so upset? That's what we have to see. Like, okay, look, here's my deal about pushing to software. You're allowed to push to software, but you have to write all the software before you make the hardware. Like, there's some things that maybe it's less of a big deal, right? So a lot of my strides are 1. A lot of my X strides are 1. No microcode. No, definitely no microcode. Oh God, no, this has strides as well. I'm upset and I want my strides. The matmuls don't have strides. Well, can you rearrange the data and always use stride equals 1? I mean, that's kind of the thought. But you can't really do that. Yeah, the strides are to access the right stuff. Can I enable discussions easily? If I can enable it, sure. Alright, I added discussions. Is it live? Cool. Now there's discussions. No, I want my fully strided shit. We're gonna figure out how to make it work. We don't want to push the software. Otherwise, I'm just the losers that are making fun of these other people for being. What's this memory access patterns? Sequential access, random access, strided, loop tiling. Well, I think if I am going to write the fully strided thing, like, maybe we don't stop at 2. I mean, if we build this thing, it's going to take a lot of silicon, so we better get a lot of power out of it. can do crazy things with, okay, so if you have like 3D strided stuff, take a look at the PyTorch abstractions for striding. It's insane. I know, I tell you, striding's the key, guys. Like I'm not, we're not going to have another struggle session. There's not going to be an ALU struggle session. The ALU is easy. It's all the striding that's hard. It's all memory. All these companies fail at memory. I mean, yeah, okay. If we're gonna commit to this striding, there's no reason it'll just be 2D striding. I can implement 4D striding. The address generation is free. All right, so we'll just have to build a big mux. Big mux. Predefined strides. Predefined strides don't help you as much as you think they do. The biggest mux on the planet. Do they have stuff in here about multiplexers? We learned a lot from this diagram. No, but it's like our fan out's really big and fan in, because like FETs and like that. Here's a 4 input NAND gate. Can I make, maybe it is only bad in FPGAs because, okay, really what these things are just like huge OR gates. No, we're not up to the ALU yet. We're working on the load instruction. To 1 mux. We need a yes. Who loves Carnot mapping? Why I don't want to use masking? Because masking's slow. You're wasting a lot of your stuff. You waste a lot of your So okay, this is all the address generation here, and like this address generation logic can be extremely complex. So we can support a whole lot of access patterns here in the hardware. That's almost somewhere you want to put in like microcoding or something. If you're going to spend all, because look at this. I mean, that's what this is. You just hide it with a for loop, but There's a topic. It's only about how to code multiplexers. So on page 140, 155. Combine pre-decoder with, yeah. So actually, if you look, see this logic here? It's like the same as this. Right? Like I wrote the same thing, except mine is bigger because 18 bits. A large binary select multiplexer is constructed from a smaller tree of binary select multiplexers. Yeah, the classic trade-off between memory usage, rearrange copy data to prepare it for the right stride. Yeah, there's a few different, tri-state and stuff. Am I in a position to actually get a chip built? What do you mean a position? Yeah, you send the HDL code, they build the chips for you. I know. Is that a troll? Do I have a chance of getting funding? Yeah, I could have fucking funding tomorrow. Capital is free. They print it. You call up your bro at the Federal Reserve and you're like, yo, can I have a couple $1,000,000? And they're like, yeah, it'll fall off the truck tomorrow. Like, I'm serious, guys. I hate this. I hate this. You people like, well, we're fucking slaves to bankers, you know? You know, you just... Like, no, the question is not, do you have funding to make a chip? The question is, do you have a chip? And no, I don't have a chip. Cruise is spending $5 billion to build Cruise Origins. Right? They're not launching self-driving robotaxis. They don't have any software that works. But they're getting $5 billion to build a lot of those things, which are completely useless. Wait, light dark bulb? Didn't I ban you? I did ban you. So yeah, I mean, like, no, money's a joke. The question is, do you have a self-driving car? And the answer is, for Cruise, well, no, but they have, you know, that. Yeah, I'm 15 and I just got offered a position in Jason Calacanis' accelerator. We have barely only launched and have almost no traction behind us. So here's VC is way too easy now in almost every industry. Yeah, like the problem is basically this: technology is largely stagnated. We haven't seen. This was in the Hacker News thread. If you look at the difference in technology between 2000 and 2010, there were huge differences. Right, 2010 era technology was actually, it looked a hell of a lot like this, versus 2000 era technology was like, oh, check out my Pentium 3, bro. So technology stagnated for the last 10 years. And there's reasons why, and I can go in, I think, to what the actual reasons are. But like, anybody who has an inkling of anything that looks like technology can get tons of money just thrown at it because money is very cheap. The problem with this is you're selecting for scammers, right? The people giving out the money have no way to evaluate whether any of the technology is good. Your friends can't raise $1 million for an ingenious startup. I promise it's not, like, what is it? It's not good, right? Like if it's good, it's so easy to get money. You also need to be the right, you need to understand how to talk to investors, right? Investors are the type of people who, like, if you go to an investor and you look to them for validation and you ask them if that's a good idea, they're not going to give you money because they have no idea. But if you come to them and you're like, look, this is going to do this and this is going to do that, you get money. George, if capital is free, why are some people homeless? I mean, that's a good question. Think about it. Think about it. Think about why. So no, the problem is not, do you have the money to make a chip? The question is, do you have a chip to make? And the answer is no. Oh, do you have a chip people will buy? Yes. I mean, tech stagnated for a few reasons. There are some fundamentals about the space that have made it harder, but also an entirely new group of people came to tech after 2010. The people from 2000 to 2010 at these companies actually knew how to build technology. The people in charge understood what building technology was. I don't really know where those people went, but you go to a company in 2020 and you get the Cruise Origin. It's morons running the whole thing, right? Like these MBA people took over and they don't understand anything about technology. So, they build Boeing in 2010 builds the 787. Boeing in 2020 builds the 737 MAX. I don't even think that they retired. I think that it's a lot of, people with my sort of attitude, but without my sort of sometimes I'll have conversations with very smart people and they'll be like, George, yeah, okay. I mean, this is all true. Yeah, they're just discouraged. They're they're not upset about it the way I am. They're just like, yeah, okay. I mean, kind of a my life is nice perspective, so why do I care? And yeah, you can have that mentality, but no, yeah, these companies, technology became this thing that was ripe for exploitation, and these total losers showed up, and they're not able to build any new technology. So that's why technology stagnated. You get the we'll take it from here types. And well, where'd you take it? I mean, you took it and they did make a lot more money. There's a lot more money going into tech in 2010 than there was in 2020 than there was in 2010. But there's no more tech. There's just more money. So, I don't know. I don't know that much about what's happening in China. Maybe the Chinese don't have these cultural problems. But I don't know what happens. I don't know what fixes this. Oh, the academics are those. They don't even have money. I can't believe what's happened to the colleges in this country. You have, again, a group of people who don't understand what knowledge is. The people running the colleges do not understand the scientific method. They do not understand the Enlightenment. And you can't fix that. No, admins took over. It's unreal. It is. Yeah. I'm doing a PhD and I hate all this diversity BS they keep pushing. Like, I'm not, when it comes down to like what diversity is, I'm not pro or anti-diversity, but I see that the way people talk about it is with zero rigor, right? Like, I'm not even judging it from an ought perspective, but just from an is perspective. These people who talk about diversity seem incredibly uninformed about it. They seem to know nothing about it. Because, again, it doesn't have anything to do with no, I even mean like whatever diversity they're talking about, they don't have a rational mind. There's so many internal contradictions in what I've heard some of these people say, and you can't. They don't respect rationality. You can't help people like that. You can just shoot them. Like, I don't know what you do. I don't know. I mean, I think that the only way to fix this really might be a war. It's upsetting, but the thing about war is war has this interesting way of, the people who built the bombs and the guns that actually work win the war, and the people who didn't, well, they lose the war, right? And then the people who lose the war, their ideas don't really spread anymore, right? Oh, yeah, so the way that you would do it is you'd build multiple, you'd have to like, not exactly bootstrap it, but you'd build like, I mean, you see my business plan, right? Like, it's first you build a cheap chip and then you build a more expensive chip. Anyone who thinks that their first tape out should be on the latest process and be like a $50 million chip is just, it's dumb. Look, guys, if they ban, I always say this, like, if they ban me, then it's really I don't think so. Like, you look at the people who are banned and like some of them, they're just trolls, right? Like, they're trolls of a different type. So, like, were the platforms right to, was Twitter right to ban Donald Trump? I mean, you can see an argument for it. I don't know. Twitter's in a tough position. Or, like, it's not clear to me exactly what you should or shouldn't do there. But yeah, look, if they ban, like, I'm a scientist. But eventually, look, if society ever bans actual rational thought, we're done. We're seriously done. I'm moving out of this country at that point. I'm moving out of wherever, man. There's got to be somewhere. There's got to be somewhere where the stuff still exists. No, I don't think Twitch should actually ban me. All right, but we're off topic again. Like, I'm not these. Oh my God, I was reading this thing from the creator of the Babylon Bee talking about how like Google and Facebook are controlling the flow of information. Do you remember like 40 years ago, if you had some like message you wanted to get out, you'd like buy an ad in the back of a magazine and say like, please mail $5 for my videotape to P.O. Box 40412. With, a self-addressed stamped envelope. Like, that was the way you would spread messages back in the day, okay? I don't want to hear Google and Facebook are controlling the flow of information. No, I don't mean to talk about politics. I do mean to talk about why technology has stagnated. And I think a lot of the problem is you have these companies who no longer need minimum viable products. I think we can summarize it as capital became too available. And the capital becoming too available led to a different group of people in technology who's optimizing for something that is not better technology. Well, the bubble will pop. Yeah? Does anyone like to live through economic downturns? I think the bubble will pop. And I think it's going to suck. Or like, that's not even like, is that something to cheer for? You can see a much better, clearer picture of it happening in the gaming industry. You know, it's interesting that you say that. I played in the World of Warcraft beta. I loved World of Warcraft when it first came out, and we've never seen anything like that. Because yeah, I mean, it turned out what was profitable wasn't like big fancy MMOs cost a lot of money to build and run. It turns out you could build mobile games that are free to play with micropayments, and they get you the same amount of money without any of the investment. So yeah, those kind of people, the people who build the addictive shit games need to be shot, right? I'm not actually saying go out and shoot people. It's a metaphor. Yeah, I mean, I don't know. I haven't played a video game really in the last 10 years. I played Pokemon Red. How could the availability of capital be decreased? Well, capitalism is meritism when it's, this... An easy way to solve this is to increase the speed of the clock. Oh. Well, Well, here's an idea. Okay. The reason it requires all this stuff. Oh, boys, I think I might have figured it out. Haha! Okay. The reason it requires all this stuff is because I'm trying to do it in one clock cycle. I don't think I have to do it in one clock cycle. What if I just okay. Let's go back to our paint. Where's our paint? Where's our little painting? Where'd our painting go? Oh, where's my painting? No, did I just close my painting? I think I just closed my painting. Okay. Paint online. Clicky. I should have taken Clicky's warning to save. All right, so what if... Let's go back to our 4x4 matrix. It's already going to take more than one clock cycle, and we have to accept that. But instead of trying to do the demultiplexing all in... So imagine we just did 4 loads, right? Okay, so we have a bunch of VRAMs, and my VRAMs really aren't well drawn. But, okay, so this one goes here. Yeah. So we connect them all. But if we accept that it's always going to take a few clock cycles, And then we like jump through the array. So we need a demultiplexer. So what are we effectively doing? We're multiplexing down. Okay. So instead of having this huge wide thing, instead of having this huge wide, 2048 by 1024, it's squared. So what if we instead made it just like 2048 by 128? And then we just like demultiplex it 8 times. I think that works. No, we don't want it square. So we have 248 BRAMs that we're multiplexing out to 128 registers. Right? Well, let's even say it's 64. Right? So then we're left with, and we do it over 16 cycles. And we demux it out 16. Right, so we're doing fetches in like, yeah, I'm adding a time dimension. That's right what I'm doing. That's exactly what I'm doing. The 4th dimension. Yeah. Well, I think we'd be left with the same crap though. I mean, because then what I want to do is, of course, like, okay, it can use 16 cycles and it can demux that array, but then, of course, I want multiple ones of these. I still feel like I could have less, though. Well, it solves the issue by, okay, if I have 64 here by 2048, like that's just a whole lot less, the multiplexer, I'm factorizing the multiplexer. So I'm rewriting 1024. So 1024 equals 16 times 64. I'm like, all right, so we have this whole thing, and then we like dispatch that and save that as one thing. No, but I guess if I have 16 of these things, it's just the same. Is it the same? If I'm making 16 2048 by 1024 multiplexers, every clock cycle would do 8 of them. And they would all like, go out to their specific places, and then it would like latch in. Let's make it 32. 32 cycles, who cares? So we're loading one array. Yeah, I'm making a big TPU style matrix loaded by risc-v. Yeah. So I load like one line. I can load one line anywhere. And we just like concat the lines. It feels like what I'm doing is basically this, right? So if it used to be 2048 times 1024, now it's 2048 times 32 plus 32 times 32, which is tons smaller. Of course, I'm not really worried about the clock cycle as long as we can pipeline everything. Like, the thing is, I would want multiple of these line decoders in order to make it fast, and then I'd end up back with, you know, oh, well, how many line decoders do I want? Well, you know, 2048 by 32 by 32, right? So, like, we're back in bullshit land. Ugh. Lower precision doesn't help. We have the precision we want. It's not. No, this doesn't really work. It's reminding me of just Google, where I'm like then shifting in these little things into the matrix. This is the memory layout for your risk. Wait, you? What? Wow. Do you have code? Oh, cool. Okay. Arbitrary precision. You know, I take you a lot more seriously if you are, wow. This is cool. What do you mean by... See, sometimes we get great people in my chat. Congratulations, you're a VIP. Wait. This is you, right? You didn't just link to someone else's project. Unless I found out you linked to someone else's project. All right. Weight memory layout is very same to feature map. Weight memory of input and output channels. Each MVU includes address generators that can be programmed to implement a series of nested loops. And you can do all these loads in parallel? No, I don't care if it's low precision, right? Like, the precision is all just like in parallel. I don't know what precision you're using, but I think the precision should be, well, I definitely want to keep the exponent 8 bits. right? So like BF16 keeps the exponent 8 bits. The problem with FP16 is it only makes the exponent 5 bits. So I want to keep it an 8-bit exponent. I'm not sure how much actual precision I need in the mantissa. So I was thinking I would use 9 bits and then 1 for the sign so I could fit it in the 18-bit blockgrams. But I'm more interested in what you did for the memory. This actually looks a lot like this status register stuff looks a lot like Apple's. Take a look at Matmul code. You might not like it. What FPGA are you using? You actually got all this to work? TVM front end? What is this? Compiler stack deep learning networks. I still don't totally understand how your memory works. Okay, so oh, it has separate RAM from what's on an X? It's a interchange format for ML models. We use it a comma, actually, if you look in openpilot. You go in models. Look, .o and an X. Well, but okay, so it seems to me you have 64 times 64 here. But your basic path here is only 64-bit wide. Okay, so one way to think about this is if we have 128 VRAMs, our data bus has width. This is the width of our data bus. And then if we're doing the other one with 2048 VRAMs, our data bus would be this size. This is the key to understanding the memory layout. Well, I guess what I'm trying to understand beyond the memory layout is like, This is your matrix unit. Oh, so 64 bits, you're doing 8-bit precision. So 64 bits is an 8-bit wide bus. Bit serial operation. I see. Okay. So your weights can be loaded in quickly, but yeah. So I have. Each clock cycle. Okay, I understand. Sponsors. Why do you say barrel? What does that mean? You have arbitrary precision with 1-bit precision. Oh, okay. See, the problem without fully strided is you end up with this. You end up with what makes all this stuff so annoying, which is that like, oh, you gotta put like your weights over here and your things over here, and you gotta like pre-stride them in memory. I don't want to have to do any of that. You evade hardware threads that share the pipeline. Yeah, I get it. I mean, yeah, I effectively want to do the same thing. It's really hard. Barrel processor. Barrel processor design. So like a Google for this? Here we go. No, okay, so I don't want to do this. I want to I understand. I mean, I wanted to build like a superscaler. I'll build a superscalar. I'm imagining almost like each line of the matrix being like a dispatch. We dispatch them and then we like fill the lines in. And each one's like a load unit that's responsible for the dispatch. I don't have to think about like the data BRAM and the weights BRAM and stuff. I want a unified memory architecture with striding. Actually, with more than striding. Mom, can we get superscalar? We have superscalar at home. At home, subscalar. Oh, that's mean. Your mom would always say you got good stuff at home when you never did. Wait, so what FPGA are you using? Did you use an FPGA yet? What are you thinking about? The AND plane and the OR plane. Unified memory architecture like Apple. Yeah, kind of. Combining a multiplexer decoder gives a binary select multiplexer. Oh, you're using Alveo. Who? Yeah, Comic-Con. Who's coming to Comic-Con? Whoa, I didn't know Xilinx made one of these. Wait, why didn't I consider this? This thing looks great. How much are they? Why was I thinking about that Alconix thing? I love Xilinx. Damn! I just like, holy shit! Okay, you know what? Who owns Xilinx? Underperforms market. It's public. I don't know. Do people know about Xilinx being an AI company? Should I just put all my money in Xilinx? How good is this card? This is great. Like, you guys see why I think this is great, right? They have a buy it now button. Of all the companies, like, buy it now. Don't worry about the price. I can't buy a graph core no matter how much money I have. You gotta suck someone's dick to buy a graph core out here. And like, not to rip on TensTorrent, but TensTorrent's like, okay, we'll give you access, George, but you have to sign this document that says you're not going to say anything bad about TensTorrent. I don't know if I'm going to say anything bad about TensTorrent. I haven't seen their shit. Like, now I'm saying something bad because they wanted me to sign something to promise to not say anything bad. All right, wait. Can we like get the documents? Where's the documents? Oh my god. And can we talk about how they didn't like force me to like sign up and like tell them about myself before I, downloaded that? I mean, this data sheet is a little light. Why was I thinking about using that other one, though, when I can use this? Buy now, docs later. No, I want more docs. More docs. Is this lots of docs? LVO platforms. DMA configuration. Platform naming and life cycle. What? Accelerator cards. Oh, this one has HBM2 as well, I see. Internal SRAM, total bandwidth. Wow! That's way more bandwidth than I was thinking. Oh, that's a sick amount of bandwidth. Are those, and that's megabytes with a byte? Oh, I love these cards. Alveo U250A. Does TinyGrad support low precision backprop? TinyGrad doesn't. I don't do anything special for it. I mean, it's really easy to add support. Find the buy it now button for Vivado. No, I don't want Vivado. Vivado for Mac. Does it run on Linux? Should I get myself a Does it run on Ubuntu? Should we get a Linux computer up in here and buy one of these cards? But I do need more documentation than this. Normally Xilinx's so good with the documentation. Why they give me this crappy documentation? What's a Xilinx DSP slice? Is this an ultra scale? No, it's an Alveo. Is it the same as the ultra scale? I don't know if these have Alveos. Can this do float? Floating point hardware. Oh. Okay, getting started guide. That's an okay number of pages. The question is, am I ever going to get my toolchain to work with them, or are we going to have to use Vivado? Can I even use Vivado? Is Alveo based on ultra scale? Yeah, maybe. Or AWS. Where's the code? First boot of what? Is there code? Where's the GitHub? Git repositories. I'm confused. There's too many repositories. I don't know if it's good or not, but I'm confused at how many repositories there are. Wait, maybe the Alveo card doesn't have a... Oh, it has an ultra scale on it. Oh, it's just a chip. Oh, it's just this chip. So I just need to find the documentation for this chip. Oh, yeah. I knew Xilinx wouldn't, yeah. No, this is still the Alveo. But it is an ultra scale. List of Xilinx FPGAs. Oh, here, so it's just this one, basically. It's the same chip as that. They just call it something else. Which is the one that's on the squirrel shit? One of the best deals I've seen on it. Oh, okay. Too much window. Too much window. Bye-bye, window. Bye-bye, window. Which is the one that's on here? VUU32P. Where's that? Is that Xilinx FPGA? Wikipedia list of Xilinx FPGA. VU33P. Okay, so that's this one. Oh, so that's like the same as like a crappy one of these. Ultra scale. That's the 280. Where's the 250? We should really add this to the blog post because these things are great. How come this one costs more? How's that one cheaper? I have to wait longer for it? I guess that has more memory. Oh, and this one has more LUTs. I'll add this to the blog post. Alveo, eh? If you want to understand what a LUT is, just, you know, it's a LUT 6, you know? There you go. SmartNIC. much is this one? How much is this one? What's the difference? It's an LV. But yeah, wow, this is the one to build, I think. This is the one to build with, I think. That's actually a really crappy number of tops, though. That can't be right. Yeah, it's probably right. Didn't the other one have more bandwidth? No, less. Wait. No. 38 terabytes per second. And this one, 30 terabytes per second. Less. It's just confusing with all the numbers. How many LUTs does my RD7? Actually, you know what? I know it from here. Or is I doing around it? Yeah. Alright, so this is 10x more LUTs. Way more than 10x more RAM. I don't know why Xilinx doesn't make this more clear. But it's this. Wow, they make even bigger ones? This is even a small one. I love FPGAs, guys. FPGAs are great. This chart definitely, oh, maybe just zoom out a little. No, it's not as bad. It comes with klebs. Which is a rebadged that. Vertex Ultra Scale. Yeah, you don't use LUTs on an ASIC, boys. Who would use a LUT on an ASIC? I mean, you can put LUTs on an ASIC, but just be noob. You know, don't do that. Oh man. Ultra Scale Architecture DSP Slice Guide. Let's learn about their DSPs. AMD struck a deal to acquire Xilinx in an all-stock transaction. So first off, this should all be illegal. But AMD, you know, AMD, Lisa Su is cool. It's Lisa Su, right? Yeah. So I wouldn't, you know, if Nvidia bought them, it's sad. You know, Jensen, take your company back from the losers. Jensen, if you ever watch this, if anyone knows Jensen, send him an email. Be like, yo, take your company back from the losers, Jensen. I don't actually know if he has power. Maybe he doesn't have power. Maybe the losers own him. Maybe the loser's got like, you know, is he married? Jensen Huang. Let's see. Is he married? Oh, he's married. Like maybe the NBA's like got a video of him like, you know, cheating on his wife or going to Epstein's Island or something. And he said to be an uncle of Lisa Sue. He owns a portion of Nvidia's stock. All right, so like not even a percent. Wow. Epstein. Yeah, no, you know, I don't even think it's Jensen's fault. I think they're holding him hostage inside that company. Poor Jensen. He doesn't want to do it, but the losers make him. Wait a second. How come this one has more of these than this one does? Andy Prietor Malt. How many of these do we have? 12,000. All right, that sounds like 12 teraflops. If we can pipeline it, what's the oath of the engineers? Order of the engineer. Like, the thing is, I don't know, maybe I'm just so cynical, and it's like, when I read this, all I see is like, I pledge to be the bitch of business people. Like, we need to kick the business people out of everything. The sooner we do that, the sooner we'll live in a nice world. Oh, I got food on my shirt. Savage. All right. Absorb information by double-clicking on it. Yeah, we're looking at different FPGAs, and we can figure out which ones we want to use. Let's see if... I don't know why I got sold on this, this one, when I can buy a Xilinx Alveo. The FK is just it's just an older Xilinx chip, which is probably more annoying to use. Like, this is probably the card. Should I buy one? Oh, of course, the one I want is... I gotta sign up for a Xilinx account. I know, it's way cheaper to buy that, and it's on eBay too, which is nice. Ah. Well, okay, I can get it here fast. Which one is this? Why don't they tell you? Oh, this is the U280. Cool, it's on eBay. Are they fake? No. Doubt it. He sells Google Pixels and Ethernet switches and stuff. Oh, I can be in debt to bankers. They're gonna make me use Vivado, aren't they? Oh, they're on DigiKey. Look at how much it costs on DigiKey. So much. Oh, is that in Canadian dollars? I don't even know how much a Canadian dollar is. Oh, good. It's cheaper in American dollars. Perfect. But it costs more from DigiKey. It's crazy that DigiKey has them, though. Are there other server accelerators? Oh, Intel makes them? What's a Terasec? Well, I'm back in Canada dollars. No Canada dollars. Yeah. Accelerating DNNs. The difference is $500. If everyone watching gave me $10, yeah, I could buy it. Wow. This is an int8. Does it only support int8s? I'm a little concerned if it only supports int8s. I don't like that. The other one supported, no, it does support FP32. At least according to this random thing, it does. Is anyone training on these? No, I don't want to. No. I don't think anyone's made training work with any of this stuff. It's 16 nanometer. Oh, that's kind of shitty. It's a 16 nanometer chip. The other one has a 7 nanometer chip. These chips really, was it 250? I'm paying that much money for a 17, for a... Is this nanometers? No. Oh yeah, I'd rather have web devs mine crypto in my browser than play audio. There's a chip wiki. Can you tell me the process? No, it doesn't. Yeah, 16 nanometer. So that's kind of crappy, but specify desired precision. No, I don't want little precision. I want big precision. Can you support floating point? Can it get me 3 teraflops? Is that what it's saying? What is this, some guy's resume? Mipsology? Oh. What's a Versal ACAP? It's 7 nanometer. Can I have 7 nanometer? Oh. How do I buy a Versal ACAP? Is this not an FPGA? Wait, guys, is Xilinx the company we've been waiting for this whole time? Oh. FP32. Why does it have an AI engine and a DSP engine? Their libraries are full of bugs. Coral AI, products dev board. Wait, is this Google's bullshit? Ugh. So you're telling me their software is full of bugs. I mean, you know, we can deal with buggy software. I don't want to use zebra quantization. I don't trust your zebra. Quantization for inference. Yeah, you can't quantize for... You can therefore implement a floating point computation. Okay, tell me more about floating point computation. Has nobody used this stuff with floating point? Why can't I find stuff? Automatic or fixed or floating point hardware generation. Look at the Vivado Design Suite reference. Yeah, because all their software is terrible. It's a nice cherry. Could be a bookmark. Blocks that support floating point data type. Custom precision. Oh. Hardware design using system generator. I will have to figure out if these DSPs can actually do what I want. Pre-adder. Multiplier. This looks like an accumulator. (48-bit accumulator, 48-bit). I have some DSP 48 E2s in my chip, don't I? So we can test them. No, I have DSP 48 E1s, and I only have 240 of them, which is kind of a pathetic amount of DSP 48 E1s. They also don't support being clocked for some reason. I mean, they're doing something. Cool. Cool. Yeah, you want to get good at stuff? This is how you get good at stuff. People, you know, you always want to know how you get good at stuff. And like, you see how you get good at stuff. You just do it. You know, people, oh my God, like the YouTube comments are like, how does George know everything about the hardware and the software? Well, you see what I do. Like, you see what I don't know. You see when I learn something new and I don't really forget it. Do with genetics. I mean, all right, some people are just dumb, but like for everybody else, it's like, you know, I know a lot of people who have the same IQ I do, and like they're not doing shit with their lives. And that's not a genetics question. It's like you can make choices, right? You have people, they're smart people, and like they just, you know, I don't know, they just don't like thinking. Or they don't want to think, or it hurts them to think, or something like that. You know? I mean, the genetics for trying? No fucking genetics for trying. Make that choice in your life, man. Like, IQ is heritable. I don't think trying is heritable. Oh, this one looks simpler. How do you do floating point with this stuff? I feel like it's just not designed really to do floating point. Like these people hacked it in. They mention floating point. It's just the same thing over and over again. Fixed configuration floating point multiplier architecture using DSP block. Wow, see, look at all this stuff you need. It's not wide enough. It would be wide enough if we had a tinier fraction. Yeah, it's not wide enough. Well, so in FP32, you have a 23-bit Mantissa. Yeah, so we'll be able to do this in one. We won't need two. We can get rid of the rounding logic. All right, so the normalization's done afterward. Iterative combined operator. Also, I think it's actually the same one twice. They just iterate it. All right. Topic. You know, you can't mention fucking IQ with you people. It matters, but not that much. No one who ever spends their life talking about IQ ever did anything, you know? You can look at, like, there was like the man with the highest IQ and he published these like weird books. IQ and conscientiousness account for like 80% of the variability in life outcome. Yeah, okay, what's conscientiousness? Right, is there a conscientiousness test? Oh my God. Guys. So destructive, you know? So destructive to society. This like myth that it like matters where you come from. Like, of course it matters statistically, but that doesn't mean it applies to you. I don't think statistics apply to you. They may not. I do hate you guys. I hate you guys who like sit around like fucking jerking off about like, if only I had 3 more points of conscientiousness. You're a loser. You are a loser. And you'll never amount to nothing with that attitude. So, if there's something genetic that gives you that attitude, well, there we go. We found out why you never amounted to nothing in life. How'd they do it with 1? How come they only used 1 DSP? And the other guys used 2 DSPs? Speed optimized Flowpoku. Iterative design. The multipliers using DSP blocks are smaller than the iterative design, but make use of 2 DSP blocks, as well as being smaller than the adder. Oh, this is the fixed configuration, and this is the iterative one. I understand. And I don't know what Flowpoku is. Multiplier DSP based. Wow. But that changes the frequency. Oh, this is cool. They're running that fast. Oh yeah, I was looking up Flowpoku. Installation instructions. Oh. Don't worry, I can just use the Docker. Docker. You found some good designs? Do they do... Yeah, I read this one, but they don't do any floating point, do they? Do they float? No, they don't float. And they probably have software that doesn't work, and they've never trained anything. No, we need float. I did like that Acronix FPGA has float. No float, and the software is trash AF. They have data flip-flops. They don't just have LUTs. Of course they have flip-flops. What FPGA you think doesn't have flip-flops? Wait, 127 LUTs to do one float? Well, let's see if that ratio works. Yeah, so we had like, what? We had 10,000 DSPs and we had like 1 million LUTs. Okay, that ratio kind of works. Floating point operator. Oh, yeah, but I looked at this one. Is this the one where they don't actually show you how anything works. They just like... Yeah, this looks useless. Alright, we might have to get FlowPoco to work. But we'll build floating point multipliers. Maybe that'll be the next stream. We didn't solve the memory problem yet. We just kind of said, like, it has to work. We didn't solve it. I just got excited about these other things. Wow, you can do it with no DSPs if you just want to use LUTs. FlowPoco just kind of seems better. Shall we return to the stride problem? Pink? You mean a zinc board? Is pink actually a thing? It's actually a thing. Yo, I love Xilinx. Okay, which FPGA is in here? Rent everything, own nothing. No. I mean, I kind of just want one of those boards. Just because it's pink. Have you ever seen a pink circuit board before? Oh, I can buy them on Newegg? Oh. That's a sad amount of logic. Well, actually, this would make a lot of the stuff easier too, because like we'd have Linux running on it, you know? Goose. Only 29,000 yen. Of course, it's not out of stock in Japan. Only out of stock in America because boats can't get here. Because like people in LA are lazy. Pink. I just want it. I want. Wait. You can connect it to a Raspberry Pi? I can connect a pink to a Raspberry Pi? Try the Newark. $46 in stock. Why are these pinks more? Oh, I guess it includes other wires. All right. Can I buy it on Amazon? That's too hard. Oh. Will I pay extra money to purchase it on Amazon because I can buy it with Prime? That sounds like the kind of thing I would do. Can I use your affiliate link? No. Oh, Microblaze. Oh, they're shitty Risk Core. Sad. I don't know. I think it's dinner time though. So it needs to play AMT to make this a complete experience. Alright guys, thank you for watching today's stream. I appreciate some of you, except for Y-fuckers and whiny IQ fuckers and trolls. But nobody ever appreciates trolls. Nobody's like, damn, I really appreciate the trolls. Look at that, it's Streamception. Nah, I gotta go find food. I'm hungry. I want dinner. Drag the face cam around. All right. Whoa, whoa! Look at that. Wow, it's you can compute the FPS by the velocity of the face cam. Wow, trippy shit, boys. Yo, I wish there were more. Oh, tendies. That's maybe what's for dinner. Nah, I'm thinking I'd order Uber Eats. I don't have any more Red Bulls. I drank all the Red Bulls. The weed harvest was pretty good. It's good weed, boys. It's good weed. Ah, please don't ever leave. Please don't ever leave. What's that from? No, what's that from, you know? Is it Drake? No, it can't be Drake. Is it Drake? No, it's not Drake. What song is that? Please don't ever leave. Please don't ever leave. Someone know that song? I don't know that song. Play a song on virtual piano. No, it's not Justin Bieber. No. You missed the whole stream. It's not Dua Lipa. Move the OBS window around. Oh, no, it gets small when you move it. You can't move it. That doesn't work. Whoa, that's pretty cool, though. Whoa. Yo, this is straight up better than like all the video games that came out in the last 10 years. Except for Firewatch and Portal 2. Whoa. Left foot, right foot, left foot slide, right foot slide. I don't care which foot, either way we about to slide. Yo, we haven't done beefing with Drake Hour in a while. We haven't done beefing with Drake Hour in a while. Outer Wilds? What's that? Oh, wait, no. I remember what Please Don't Ever Leave's from. It's Battle of Hampton Roads. Yeah. Oh, yo, you guys, this is a great song. Solidarity's gonna give a lot less than it takes. Is there a girl at this college who hasn't been raped? Is there a boy in this town not exploding with hate? Is there a human alive who ain't looked themselves in the face without winking, or saying what they mean without drinking, who will believe in something without thinking? What if somebody doesn't approve? Is there a soul on this earth who isn't too frightened to move? Bye, everybody.